All right, example one. Example one just has a couple radicals that we are going to simplify. So there's really no instructions here, but the instructions should say something like simplify these things. And so for the first one, I have the square root of 75, and I want to reduce that to its lowest form. Now we actually did this in chapters kind of like 5, 6, and so this might be a lot of review, which is not a bad thing. So the square root of 75, what I'm trying to do here is I'm going to use the product property and break this up into two separate radicals, two things that multiply up to 75. Like for example, 25 times 3 multiplies up to 75. So I could write this as root 25 times root 3. And the key here is that one of those is a perfect square. So the square root of 25 comes out as 5, right? So that comes out as a perfect square. And the square root of 3 cannot be reduced anymore. So this would just stay as root 3. And my answer, in order to reduce that radical, is going to be 5 times root 3. So we can use this product property to break up a radical in such a way that one of the factors is a perfect square, and that we can pull out these numbers outside of the radical, kind of like what we did in chapter 5 and 6. All right, another example here, we have root 100 over 169. This one, we would want to break up and first use the quotient property to say square root of 100 divided by separately in the square root of 169. Now, when we do that, it just so happens that these numbers are perfect squares already. So the square root of 100 separately is 10, and the square root of 169 is 13. And so that one simplifies quite nicely because the top and bottom were already perfect squares. But notice again that we're using, here we use the quotient property to break this up. And the one above, we use the product property to try to reduce that. All right, another problem here is the square root of 7 times the square root of 35. And again, all we're to do here is to simplify as much as possible without just plugging this in and getting a decimal approximation. We want to keep this in exact form and keep it in what's often referred to as simplest radical form. Let me write that down. Simplest radical form. So we have a root 7 times root 35, and what I would do here is simply combine those to start. By using the product property, we can say that this is going to be the square root of 7 times 35. So 7 times 35 is going to be 2, 10, and 35. So 245. 245. And so we combine that into one thing. But now, we're going to re-break this up and say, well, this is going to be equal to, we're going to use the product property to break it up again. But this time, think about the number 245 and think about if there are perfect squares inside of 245. So 245, you could use a calculator. You can do this a couple of different ways. Think about a perfect square. Think about all your perfect squares here. Let's think about these. Perfect squares would be, like 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, we have 36, we have 49, etc., etc. Trying to think about, are any of these numbers right here factors of 245? Do any of them go into 245? And so if you do a little experimentation and you try to divide 245 by any of these numbers, you'll see that 49 actually goes in there. So 49 times 5. So 49 times 5 is 245. And 49, of course, is a perfect square right here. So that is going to be reduced quite easily. And then we'll have root 49. Well, that's, of course, just equal to 7. And so this will become 7 root 5 for that problem. All right, so here are a couple practice problems that you can just pause and see if you can do. I'm going to show you how to do it another way, just in case this one makes more sense to you. But so for letter A, we have the square root of 150. What you can do with root 150 is simply just take the number 150 and you can just start factoring it just by doing a prime factorization. It's basically doing that factor tree that you've done before with any number. If you have 150, just think about any number that can go into 150. So I know that, for example, 15 times 10, right, would work. And I could just keep on breaking this down. So 5 times 3, 10 is going to be 5 times 2. And basically break it down into its prime factors all the way down to the bottom here. And so now what I would do is these numbers below are all the prime factors, meaning if I took 5 times 3 times 5 times 2, that equals 150. But really we want to look for things that are squared. So I could rewrite this. You can see we have 2 5s. So I could write this as 5 squared times 3 times 2. And so since this 5 right here is squared, I'm going to be able to pull out a 5 of the square root. So in other words, if I took this, and again I go back to this problem of the square root of 150, right? The square root of 150 is equal to square root of 5 squared times 3 times 2. We just factored it. Anything, because this is a square root, anything that is squared, like that 5, is going to be pulled out of the square root. You might remember that from like chapter 5 or 6. And so now it's easy because all we have to do is say, all right, this 5 is going to come outside of the radical, and what's going to stay inside is anything that's not squared. So this 3 times 2 is going to stay inside, and I get 5 root 6 is my answer. Now you could have, of course, someone else might have done that problem and said, no, there's a way easier way to do that. Just break it up as 25 times 6. And this is going to become 5 root 6. Either way you do it is completely fine. It doesn't matter which way you do it. There's going to be pros and cons to those methods based upon the problem that you start with. Sometimes it's easier to do one of the methods over the other. But again, pick the one that's easiest for you and go with it. So let's do the second one, root 200. Okay, so again, you could do a factor tree, or you could just think about, well, what times what is 200, and try to think of a factor that's a perfect square. Personally, I would just think about, this one just seems like an easy one because I can just think of 100 times 2. Right? I know 100 is a perfect square, so if I just say 100 times 2, the square root of 100 is 10, so I know this is going to be 10 root 2. Now if you did it the other way, not that you need to, but if that way, if you like doing it that way, because it's very predictable, it's very mechanical. 200, if you start breaking that up, you can just say, all right, well, let's say we did 20 times 10, and then, this is going to take a little bit of time to get down to the bottom here. Right? This is 5 times 2. So all these numbers are the prime factors, and so now we have, this is basically any pair that we have is going to come outside of the square root. All right, so if I write all these down, 5 times 2 times 2 times 5 times 2, anything that is paired up is going to come out. So I'm gonna group these as perfect squares. See that I got a 5 times 5, so that's 5 squared, times I got a 2 times a 2. I'm going to write this as a 2 squared, and then I have a leftover 2. So again, if I took the square root of this, if I took the square root of 5 squared times 2 squared times 2, you could see that a 5 would come out, a 2 would come out. I'd have 5 times 2. And then this 2 right here doesn't have a exponent of 2 with it, so that would stay inside of the radical, and we would get the same thing as 10 root 2. Now, of course, you're probably thinking that first method was just way easier, so why would I do this factor tree? I just had a lot of students that have showed me both ways, and they always ask me, can I just do this factor tree? I learned it like this, or it's easier for me. So it doesn't matter which way you do it. Just pick a way that's easiest and go for it.